Chapter 1, which is largely a review, signals and amplifiers. We are going to be going through this chapter relatively quickly, much more quickly than we are going to be, than a pace we're going to be using for other chapters and moving forward. There's going to be certain parts of this chapter that I'm not going to provide every detail on. I'll explain some things I may not be testing you on, some things I may be expecting you to recall from earlier classes. But in short, this is sort of like the warm-up to get us into chapter number 2. So I'm going to try to do it in a rather efficient manner. Each chapter has a little bit of an intro, and we talk about what we're going to learn. So in this chapter, we're going to be talking about signals and the processes that are applied to signals. We're going to be talking about Thevenin and Norton representations of signal sources. Again, that should be something that sounds very familiar. We're going to be talking about representing a signal as a sum of sine waves, which is what we call a Fourier series representation. We're going to talk about analog versus digital. We're going to talk about signal amplification, how amplifiers can be characterized, and then a little bit about frequency response and some basics of filters. Again, filters, another thing that you should have learned about in ENG212. I know you do some labs on it in ENG214. One last note, housekeeping issue. Hopefully all of you are enrolled in the lab, the ELC333 lab, the electronics lab. If you're not, come talk to me after class and we can see what the situation is. It doesn't have to be taken with this class. It can be taken later, but you will all need to take it. All right, so moving on to signals. So what's a signal? A signal is anything that contains information. The most basic old school example is the voice on a radio, right? Announcer reading the news. A process is an operation which allows an observer to understand this information from a signal. Generally, this is done electrically. And lots of things can fall into this bucket. It could be amplifying the signal. It could be trying to remove noise from the signal, filter it in an appropriate way. If you get into more advanced stuff, it could be encrypting it or decrypting it. Or even, let's say, the process of transforming it from a DOC file to a visual representation which is shown on your computer screen. A transducer is a device which converts a signal from a non-electrical to an electrical form. The really popular example is always the microphone, right? The microphone, what it does is takes my voice or anyone's voice, vibrates a diaphragm, and that converts it to an electrical form, right? The resistance of the diaphragm changes as it vibrates. I have to use this as a microphone today because I forgot my little lapel thing, so that's the reason why I'm carrying my phone. So microphone, another example would be a digital camera, right? A digital camera converts the view into individual pixels, which are represented digitally. How are signals represented? This should look very familiar. We have a Thevenin form as well as a Norton form. A Thevenin form is a voltage source in series with a resistor. A Norton form is a current source in parallel with a resistor. And here we have the figures. Again, nothing new here. We know from ENG212 that we can go back and forth between these two forms. We know from ENG212 that we can represent any circuit that's linear and is composed of passive sources, passive elements only, can be decomposed, or not decomposed, but can be represented as the equivalent Thevenin or Norton circuit. We're not going to talk about that in depth here, but just something to remember. Example 1.1, I'm going to ask that you take a look at on your own. It's just a really, really basic example asking you to calculate the output versus the input for these two circuits that are shown. One, what's the left-hand side? What does that look like? Hopefully you guys, there's a name for that circuit on the left. Voltage divider, exactly. And then the right-hand side, current divider. And so the relationships between the output and the input for those should be very familiar. Output is equal to the input or the source times the load resistance over the sum of the two. And so what we see is that the question asks you, when do you have maximum power output? And what is the ideal value of RS? And so what we see is that we want for this to be equal to 1, meaning that our output is the same as our input, because that's the highest it can get, right? The output can't get higher than the input. It's a passive system. And for that case, ideally, RS must be much, much smaller than RL. The main takeaway here is hopefully this type of stuff looks really familiar to you. If it doesn't, then you may have to take a look back at some stuff from ENG212. This course relies a lot on ENG212. Let's say you start off a problem that has to do with diodes. We take the diode problem, we try to reduce it to something that is composed of only resistors. We could use a small signal model for that. I know you don't know what that means yet, but the last step of that problem has to be solving it. Okay? So if you are not as strong as you need to be on that part of it, how to apply KVL, KCL. We're not necessarily going to be doing really large circuits that are going to require nodal or mesh analysis. You can use those, but maybe it's not as heavily applied here. But if you can't apply KVL, KCL, analyze the basic voltage divider or a current divider, you're going to have a little bit of trouble. So then I would recommend coming to talk to me. I can give you some pointers on materials to review to get your ENG212, your circuit analysis skills stronger a little bit. This is a good time to do it now before the material gets a little bit more difficult. So the second part of this problem asks you to do the same thing with a current divider. And so you can see this is the relationship, hopefully, that you're all familiar with for the current divider. And ideally for the current divider, the opposite applies. Okay. This chapter is, for better or worse, topics that are relatively disjoint from one another in series. So we jump from Thevenin and Norton equivalence to frequency spectrum. So what is a frequency spectrum? Without reading what's on the board, can anybody tell me what that means to them? How do we represent a signal by its frequency spectrum? What is that really saying? Anyone? So we all know how to represent a signal in the time domain, right? It's what you see on the oscilloscope. Let's say it's a square wave. It looks like this. X-axis is time. Y-axis is voltage. Okay? There's also a frequency domain representation where we define the signal in terms of the strength of its harmonic components. So if I have this square wave, I can represent it as a sum of a whole bunch of sine waves of different frequencies and of different amplitudes. It may take a lot of sine waves added together in order to get those really sharp curves or really sharp angles, but we can do it. So an expression, so for that we use what's called a Fourier series decomposition. This is an expression of a periodic function, like a square wave, as an infinite number of sinusoids whose frequencies are harmonically related. It doesn't necessarily have to be infinite. One of the examples we're going to look at in this class, the strength of the harmonics drop off, meaning that after like the 20th or 25th harmonic, you could probably stop adding. But ideally, infinite. Now, what does it mean when we say that the frequencies are harmonically related? It just means that they are integer multiples of one another. So if we start off with a base frequency that's 200 hertz, then our k equals 2 harmonic will be 400, k equals 3, 600, 800, right? Going on and on. So this math here looks messy, but it's actually, if you pick apart the individual pieces, you'll see it's just saying the exact same thing we saw on the previous slide. So let's say we have some periodic function that we're calling f of x. Forget about this term for a second. we can represent it as a sum of, so cosines and sines are both sinusoidal, so a sum of cosines whose frequencies are harmonically related, right? Because what we're doing is we're multiplying a k times the x. The x is the omega t. So you're really, by multiplying a k in there, we're increasing the frequency by 1 times, 2 times, 3 times, 4 times. And each one of the cosine waves for each harmonic has its own height, right? That's really how we control the shape of the output. Because the sine waves and cosine waves, they all have the same shape, right? But it's the combination of which ones are big, which ones are small, which ones are non-existent. That's how we formulate the output. So each cosine has a coefficient or an amplitude that's assigned to it. And so when we sum all these together, we get the output. Now for the Fourier series decomposition, we're going to use cosines and sines. This is because we're not including a phase shift, right? The cosines and the sines together account for the phase shift. And then lastly, what's this here? This is the Deese offset term, which moves the thing up and down. Now, I'm not going to go deep into the math behind doing this. And the reason for that, number one, this should be covered in your signals and systems class. Number two is that I'm not going to be testing you on this in terms of asking you a mathematical question. I'm not going to give you a signal and ask you to do the Fourier series decomposition for it on either one of the midterm or final exams. However, we do need to understand frequency spectrum, and we do need to understand frequency response. And so at least going through this in a high level, looking at it from a high level, is going to be important in order to do that. Now, what are the two red equations below? The two red equations below are how we get the A's and the B's, because that's really the hard part of this problem. If you have all the sinusoids, adding them together to give the output, that's not that bad, right? You just sum them together, make sure to multiply the right coefficient by cosine or sine. Okay, it's not that bad. But going in the other direction is more taxing, it's more difficult, and you have to use integrals in order to do that. So in order to come up with our A value, we have to multiply 1 over pi times the integral over a single period of the signal we're trying to decompose times cosine kx dx. Then, to get the B values, we do something similar, 1 over pi over a single interval, f of x sine kx dx. And so we're going to go over a very basic example of doing that. Like doing any integral, right? It depends on the type of signal that we're looking at. And this is not a calculus class, so we're not going to go into really, really complex examples. We are going to start off with one that's relatively easy to integrate, and that's a square wave. So how do we calculate the Fourier series decomposition of this square wave shown here? The nice thing about the square wave is that the integral will be relatively easy because, right, it's piecewise. We'll split it up. The integral here will just be integral of a straight line or a single value times cosine. Single value times cosine. Single value times sine. Single value times sine. Okay, so let's jump straight in. First thing we're going to do is apply this right here. And now we're going to plug in our square wave for the f of x. And what we end up with, like I said, is something that we can split up into two different parts. If you're really unfamiliar with Fourier series decomposition, I do recommend you take a look at this, both either in the textbook or in the notes. It's really just 2 or 3 steps in order to take the definite integral. So we split up into two parts. Between negative pi and 0, the value is negative VA, negative amplitude. And between 0 and pi, it's positive, right? That's where it flips from negative to positive. And actually taking the integral is not that bad. What we end up with is 0. AK equals 0. So that goes away. Then we move on to get our sine. And so, or our B value. Same thing, we split the integral up into two different parts, piecewise representation. negative VA, positive VA. These are the two intervals. We go through all the math, and what we end up with is a BK value, which is 0 whenever it's even, and it has this value here whenever it's odd. It'll be equal to 4 times the original amplitude of the square wave divided by k times x, where k is the harmonic value. So what does the response look like? Looks like this. So this is how the frequency spectrum is represented. The x-axis, as opposed to being time, is the frequency of the harmonic that we're talking about, of the sine wave that we're talking about. The y-axis is the magnitude / the strength of the harmonic. So the way that this math worked, or the way that this solution worked, is we see that it decreases with a rate of 1 over k. So this is a nice one, because if we wanted to represent a square wave well, you could see that it'd be easy to cut off, at a harmonic of, 30 or 40 or something like that. Again, if you want it to be completely perfect, you have to go for thousands or, infinite number of harmonics. But this is a nice case where we have the magnitude of the harmonic reducing. So this is the main takeaway I wanted from this example, is for you to be able to understand what this means. So if you see another problem where a frequency response is represented, this is not a frequency response, frequency spectrum is represented in this manner, you understand, okay, this is the base frequency, third harmonic, fifth harmonic, seventh harmonic, and the individual strengths. Now, how do we create the signal mathematically? Right? We do this. This is the original form we were given. We know that AK is equal to 0 for all K. And we know that BK is equal to this for the odd ones only. So what you end up with, this is an intermediate step, but what you end up with is down here. We have 4 times the amplitude of the square wave divided by pi sine omega naught t plus 1 over 3 sine 3 omega naught t plus 1 over 5. So you see there, again, there's only the odd harmonics that are shown. We only have sine waves and no cosines because our A dropped out. And because our A dropped out, we also have no DC offset term because that piece went away. Okay? So this is the mathematical representation of what we have right here. Frequency spectrum, frequency domain representation of a periodic signal. All right. Hopefully you all understand what a sinusoidal wave is, what the different parameters are. Obviously, there's the amplitude, there's the period, there's the frequency, there's the phase shift, right and left. There's also the root mean square magnitude. The formal definition of the root mean square is square root of the average of all the data points squared. But the nice thing is there's a shortcut for sine waves, right? For sine waves, we can just take the amplitude and divide by the square root of 2. So really, we rely on that shortcut a lot because 95% of the time we're dealing with square waves. Sine waves. Okay. Can the Fourier transform be applied to a non-periodic function of time? It can. The main difference is that instead of having the pulses at the individual harmonics, you'll have a continuous function, meaning that you have to define sine waves at 200 hertz, 200.1, 200.2. You have to essentially fill the entire spectrum. We're not going to be talking about this case. We're going to be focusing predominantly on periodic functions. All right. So shifting gears a little bit again to talk about analog and digital signals. So let's throw this out to you. what's the difference between an analog and a digital signal? Sure, you were all familiar with the terms, right? You must have some. If someone on the street asked you, you'd come up with something. So I throw out the terms old and new. Which one's old? Analog. Which one's new? Digital, right, okay. I throw out the term like record player, computer. Which one's the record player? Yeah, computer's digital. So you have some idea of what the difference is. It's just a matter of trying to describe that in a more formal way. So an analog signal is one that's continuous with respect to both value and time. Record player, right? A record is a scratch on a piece of vinyl. And you can zoom in and zoom in and zoom in with respect to time and with respect to value, and you'll keep getting more and more levels of detail. I mean, within a certain practical level. Same thing with the old type of picture, the film, you know. You can keep zooming in and magnify the picture. Again, before you start to run into the physical constraints of the film. So what about a digital? A digital signal is quantized with respect to time, it's quantized with respect to value and sampled with respect to time. We'll talk about specifically what those values mean in a sec. But like an MP3, right? An MP3, if you keep zooming in with respect to time, eventually you're going to see there's gaps in between the individual, moments of the song. If you have a digital picture and you keep zooming in, you'll see the pixels, right? It's quantized on the pixel level. And that's the reason why we talk so much about resolution when it comes to digital signals. No one used to ever talk about resolution when it came to records or pictures, even though I guess they do have some finite resolution if you get down to like the molecular level or something like that. But this is a digital, a value that's mainly important for digital signals. So analog signal continuous with respect to both value and time. Digital signal is discrete with respect to both. And then we have a discrete time signal, which is sort of in the middle. And the following picture will give a better description of that. So let's say we take this analog signal here. How do we go from an analog signal to a discrete time signal? It's a lot like taking a knife and like chopping up, some piece of vegetable or something like that. You just say, okay, our sampling rate or our sampling period is going to be 1 millisecond, and so every 1 millisecond I'm going to take the value. Everything else I'm going to throw away. So even though you see the blue line in between these points, when you take a discrete time sample, anything that's between two black lines is gone. Now, how do we go from a discrete time to a digital signal? Over here, this value is the exact same value as the one above it, okay? Let's say it's in volts, 3.26598, whatever volts. That's going to be relatively difficult to represent in computer memory or some similar type of construct. So what we're going to do is we're going to quantize it. Quantizing is when we essentially round. What we say is that our values, we're going to set a resolution. We're going to say the voltage we'll have a resolution of 100 millivolts. And so we'll knock it up or down to whatever the closest 100 millivolt value is. If it's 125 millivolts, we'll knock it down to 100. If it's 175, we'll push it up. I mean, there's different algorithms for doing this, but that's the basic gist. So sampling, we cut in the x direction. Quantization is not necessarily cutting in the y direction. It's taking the points and pushing them up or down to be in the closest bin. Now, why do we do that? Why not just leave it the way that it was? It was fine on the left-hand side. Why do I have to quantize it? Yeah?
Because you can't be infinitely precise with a limited amount of bits.
Exactly. That's a perfect description, actually. You cannot have this infinitely accurate number represented in memory unless you have, same thing in base 10, right? If you want to have an infinitely accurate number, you need to have an infinite number of digits following the zero. That's going to be really hard to store, okay? Even if you're doing it by hand, you still are going to have infinite sheets of paper. So By quantizing, what we're doing is we're setting a cutoff in terms of accuracy, and we're saying, okay, we care about accuracy up until this point, and then past that, whatever. Okay? More resolution in sampling, higher resolution will mean better signal quality. Same thing here, higher resolution with respect to the bins that we use for quantization will mean higher signal quality. Will mean that what we get out is closer to what we get in. Higher sampling rate means that we'll have to store at more memory addresses. Higher resolution on the y-axis means that each memory location will have to be bigger because we'll need to store more bits or more digits. Now, we haven't even talked about base 2 yet. This could all be done in base 10. Okay, you could design some sort of a machine that stored everything in base 10, but still employed sampling as well as quantization. So you could have a digital signal. Now, why do we store the signal in base 2, in binary? Well, our computers rely on that because our computers, digital computers, are all switches, right? On, off, 0, 1. That's all they know how to do. So by default, right, if we're going to take the digital signal and store it in our modern technologies, we need to put it in base 2. So digital and binary are not necessarily synonymous. They largely are in practical terms, okay? If someone asked me, is a digital signal binary, I'd probably say yes because I understand what it is that they're trying to say, but the words don't necessarily mean the same thing. Now, how do we go from base 2 to base 10? I'm not going to spend a lot of time on this. Let's talk a little bit about base 10. So let's say we have a base 10 number of 111. Right? What does that really mean? You have 3 digits. The 1 all the way to, well, the least significant digit, right? Is what that really means is you're 1 times 10 to the 0, right? 1 times 1. That's the first digit. The next digit means 1 times 10 to the 1, right? That's 10. So you have 10 plus 1. Then the most significant digit is 1 times 10 squared, which is 100. So you have 100 plus 10 plus 1, which gives you 111. All right? Base 2 works the exact same way. You have digits which can take on the value of either 0 or 1. And if you want to convert it to base 10, you multiply by 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, going on and on and on. And so this would give you a conversion between base 2 and base 10. And there was that one video in the suggested videos that talked a little bit more about the differences between digital and analog. So if you want to take a look. All right, shifting gears again. Signal amplification. So why is signal amplification needed? Because a lot of times our signal is not going to have the resolution that we want, meaning that if you look at it on an oscilloscope, it's so tiny, you can't see what's going on. Or it may not have power needed to drive whatever the load is. If anyone has ever taken a regular old microphone and plugged it into, let's say, a speaker, okay, that's not plugged into the wall, you talk, nothing's going to come out because the amount of power that your voice generates in the microphone is not going to be enough to shake the woofer of the speaker or the diaphragm of this big speaker. That's why you need an amplifier, because what the amplifier does is it adds more power to your signal and boosts the current level. Let's say you're trying to record with that microphone something that's very soft. Then you may need a voltage amplifier in order to make the amplitude of the signal bigger. So there are amplifiers that can do both. They both fall within the same range, but they have slightly different purposes. There's voltage amplification to increase resolution. There's power amplification to increase strength or intensity. Now we talk about linearity and distortion. We always say we want a linear amplifier. Can anybody tell me what does that mean? What is a linear amplifier, a linear device, a linear process? There's lots of different ways of describing this. Yes?
whatever's going in is the same, like a proportion of what's going out?
It's actually a very good description, yes. Shape stays the same. That's the best layman's description I could give. If you put in a sinusoid, you get out a sinusoid. If you put in a triangle wave, you get out a triangle wave. You can make it taller and shorter, you can do a couple other things to it, but you should be able to recognize the shape. And that's important because the shape is, if you talk about sound, is essentially what determines the tone and what you understand. If you change the shape, the song is going to sound differently. You can boost the signal and it'll still sound the same, it'll just be louder. But you can't change the shape. So what is distortion? Well, to go back to linearity for a second, the more formal definition goes back to superposition, additivity, homogeneity, essentially this idea that the process that we're applying to it fulfills those mathematical requirements. So distortion is any unintended change in the output. So a nonlinear process would distort the signal. There's other types of distortion as well that are not related to linearity per se. There's noise, right? You could just have a noisy process, a noisy device or a transducer, which, inserts high frequency, low amplitude signal in there that's just random. Anyway, there's lots of different types of distortion. But, right, our ideal is to have a process that is highly linear with very low distortion. We talked about this already, right? There's a voltage amplification and there's power amplification. Both are often needed. Both play different roles. Voltage amplification is going to be more important when you talk about things like instrumentation. Okay, if you're working with computers and data, often, right, that's what you're more worried about. Is the resolution appropriate for the application that we're looking at? Power amplification is more about driving loads. So let's say you're building a motor controller, right? Amplifying the control signals appropriately to be able to drive the motor would be a huge issue. If you're, talking about radar, amplifying the signal so they're strong enough to produce the desired result. Obviously, if you're working with audio, that would be important. Okay, gain, how may it be expressed in decibels? Decibels is a logarithmic description of gain. And what you'll see is that there's three equations up here. The top two are the same. The bottom one is different. So voltage gain in decibels is simply just 20 log base 10 times whatever the gain is. Current gain, same thing. Power gain, there's a difference. The coefficient is 10 as opposed to 20, and the reason for that is because the coefficient needs to be different in order to maintain voltage times current equaling power. In this class, I'm not going to ask you to memorize a lot. Okay, my goal is for you to be understanding or learning stuff for comprehension and know how to use the tools that are in front of you. So you will have a cheat sheet. Those of you who had me in ELC251 know I provide a pretty long cheat sheet. You'll have those for all your midterms, and that'll have equations like this on there. So be familiar with the equations. Know how to use them. If I ask you something for something in decibels, a bell should go off in your head, saying, "Okay, I know what I gotta look for this equation." But you don't necessarily have to memorize it. This is one you probably should memorize, but later on, not so much. Okay, so conservation of power efficiency, really all that's saying is, an amplifier works like any other physical system. It conserves energy. So the amount of power that's being applied to the load or being supplied to the load plus whatever's lost to heat will be equal to the power of the signal coming in plus the power of the DC supplies that are being given to it. So if you look at all the different terminals, all the different ways of power going in and out of the system, they should all sum to 0. The signal inputs, the DC inputs, the main output, and then heat, which is not necessarily shown on the electrical diagram. Efficiency is the ratio of the power output to the input. So if the P dissipated is 0, efficiency will be 100%. As that gets larger, this ratio will get smaller. Okay, amplifier saturation. So this is one of the really comprehensible, non-linear behaviors that we see. You've already seen it. You saw it in ELC251 in the circuits lab. When you were working with amps in that lab, it couldn't work for an infinite range, right? There was a limit that the output worked on. What was it normally? Yeah, the supply voltage essentially dictated it. So we were often using like -15, +15, -12, +12, whatever that is. So the output of the amplifier couldn't go past that. And really, if you want to be more specific, the linear range ends a little bit before that. Because as you get close to the rails, stuff starts to get a little bit curvy, less linear. So let's say your supply is 15 volts. Your linear range ends probably somewhere around 12.5, 13 volts. So what is this equation saying here? It's just saying that, okay, your voltage input, in order to generate a linear output, needs to be in between -15 divided by whatever the gain is, right? Because that's the output has to be between -15 and +15. The input has to be between -15 and +15 divided by whatever the gain is. And if you stay within that range, this limited linear range, you should observe a linear process. And then when you go outside of that, you see what's called saturation, which essentially is when the thing flatlines, right? Let's say you try to amplify let's say the gain is 1, which makes the input and the output the same. That's easy. So the gain is 1, and you take a sine wave that has an amplitude of 20 volts, and you supply it to an amplifier that has a supply voltage of 15 volts. What are you going to end up with, right? You're going to end up with a sine wave where the tops and the bottoms are chopped off, right? Once it gets to 15, it'll stop, stay at 15 until it starts to decrease again. All right, this is your first homework. It'll be due a week from today. Again, do it for comprehension. Please bring it with you that day. And if I collect it, I'll be grading it for effort. So all eyes, everything should be focused on that first midterm. That's really what you're looking toward. Okay? And doing as much as you can in class, outside of class, in order to maximize your chances of doing well on that. Anyone who's had me in class before knows I base my exam problems off of homeworks and examples heavily. Okay? That doesn't mean that I don't copy the problems or anything like that, but I mean, if you are good at doing the homework problems and good at doing the example problems, you should, when you see my exam, it should be like ringing bells in your head, like, oh, okay, this is part of this problem. I remember this method. So there's a lot of benefit. There's a lot of bang for your buck and payback in terms of taking the homeworks seriously. Again, the solutions are already provided, so you are doing it for your own benefit. Okay, so models. A model is a description of a component's terminal behavior. There's lots of different types of models for lots of different types of things. Okay? And it's really hard in many cases to say what's a good model versus a bad model, a right model versus a wrong model. A lot of times it depends on application. We can represent a diode, for example, as just open circuit, short circuit. Or we can define the model for a diode as this exponential function with all kinds of different parameters and terms. Both are good. Both are right. Both are very useful. Okay? I don't know if I use this example yet, but again, it's the whole thing with the toaster versus, the MRI machine. It really depends on what the application is. So the model describes the device's terminal behavior, neglecting internal operation and really the transistor level design. Sometimes a model could be modeled after the internal behavior. That's one way of modeling something, okay? But it doesn't necessarily have to do that. So one model that we worked with in ELC251 was this for an amplifier. Now, when we get into examples and math that are more in depth, I will pull out the iPad and write down things and go more in step by step. But there's not any of that in this first chapter. And hopefully stuff like this should be familiar enough that you recognize what's going on. So let's take a look at this picture and let's try to figure out what these equations above mean, how they relate to it. Okay, so this is an amplifier. The part in the blue is the actual amplifier, or the representation, the model of the amplifier. This is our source coming in. This is our load that's being driven, right? So what do these look like? What does this look like? What does this look like? Right, what type of circuit is that? We said the name earlier today. Voltage divider. Okay, good. So we can do this quickly. So what's the mathematical model for this left-hand side? VI, which is over here, will be equal to RI divided by the sum of these two together, times whatever the source is. So voltage divider, left-hand side. Right-hand side, again, voltage divider. V out is equal to the source, which is a dependent source, times RL over RL plus RL. Again, voltage divider. How do we combine these two together? Well, this is a dependent source, which is dependent on VI. So this is the same VI as right here. So we can take this whole thing, put it inside of here, and what we end up with is this. So the combination of both them together gives us our gain value times VS times these two ratios. And so it has a lot of different parameters. Is this normally the way we want our amplifier to work? What's the problem? So we want our gain to always be the same. We don't want our gain to be dependent on the load. Okay? The load can, especially if you're working with certain types of devices, the load can fluctuate with the signal. Okay. We also don't want it to be dependent on the type of source that we're using. Right? That would be like having our iPhone do all kinds of crazy stuff depending on what type of headphones we plug in. So what we want to do is ideally we want V out is equal to a constant value times Vs. And so how do we do that? We need to make these equal to constants, these two ratios. So we talked already about the ideal values. What we see is that ideally we want our Ri to be much bigger than our Rs, because this will simplify down to 1. The rule of thumb that I'm going to use is 2 orders of magnitude larger, meaning that if our Ri is 1,000 ohms, we better have an Rs that is less than 10 ohms, 100 times smaller than that. Over here, our RO, let's say that's 100 ohms. Then our RL better be at least 10,000 ohms, 100 times larger than that. Now, this is not just some textbook question. This is something you'll really use if you're trying to design a system that uses amplifiers because, okay, you're trying to drive some load, you have some source, you're looking for an amplifier. You look in the data sheet, it's going to give you specified values, rated values for the input resistance as well as the output resistance. You have to go and make a judgment call. Okay, is this amplifier good for the application that I'm going to be using it for based on impedance matching characteristics, right? Do our RL and RO values, do they work together? Do our RI and RS values work together? Is it going to provide me the level of linearity that I'm looking for, a constant gain between the input and the output? So the ideal model, after we make those assumptions, looks like the second version of this. So if Ri is much larger than Rs, it is going to be, essentially, it's going to look like an open circuit, right? Meaning that no current will be flowing into the amplifier. That should sound familiar. Talked about that a lot. ELC251-01. And then also, we'll see is that the output resistance will essentially be a short circuit. And so for this representation right here, V out is equal to our constant gain times Vs. So that's a quote-unquote good or linear version of the amplifier. RO should be much, much less than RL. RI should be much, much more than RS. So those are the key characteristics of an ideal voltage amplifier. Source resistance and load resistance have no effect on the gain. Okay. Now, this is one topic that's a little bit new, so we are going to spend some more time on this. This is going to come up in homework problems a lot. Cascading amplifiers. So in real life, an amplifier is not necessarily, first off, an amplifier is not ideal, right? It's never ideal. And you're not always going to be able to find the amplifier at the cost that you're looking for that fits all of your needs. Okay, maybe you find one that has the right output resistance, but the input resistance isn't good enough, or vice versa. So what do you do in that case? Cascading of amplifiers is, what it means is using them in series. And so we can use a first amplifier, which interfaces with the source, that will have a very high input resistance. Maybe we don't care about the RO. We'll have a final amplifier, which will interface with the load, and that will have a low RO, but let's say the RI value is not that great. And we could have amplifiers in between that help us in other ways, mainly to boost the voltage, to boost the gain even greater. Maybe both of these together still don't give you the gain that you're looking for. We can throw another amplifier in the middle in order to boost that. So the aggregate has a really good high input resistance, has a really good low output resistance, and potentially has the high gain that you're looking for. Okay. Example 1.3. This is from the textbook. Cascading amplifiers. So we're going to take a look at a system in a second. And what we want to do is we want to calculate the overall voltage gain, we want to calculate the overall current gain, and we want to calculate the overall power gain. But to tell you the truth, once we calculate the first one, the rest will fall into line because we can just use Ohm's law to solve the second and the third parts. Okay? So let's take a look at the system. Looks like this. So what we have in between the blue dotted lines, this is the first amplifier, this is the second amplifier, this is the third amplifier. On the right is the load, on the left is the source. So let me ask you, is this a good setup with regard to the source and the output and load resistances? So the ratio between the input resistance and the source resistance for stage 1, there's only a factor of 10, but I guess that's the rule of thumb they're using, so it's good. At least it's not closer than that. And then for stage 3, again, factor of 10 separation. The output resistance is 10 times lower than the load resistance. 10 is 10 times lower than 100. Okay, so this is the example they're giving us. I'm going to say, okay, fine, we'll go with it. That's good enough. If I were designing it, I'd probably ask for a little bit more separation, but anyway. So now how are we going to solve for the voltage gain? What we're going to do is essentially the same thing that we did for that little mini example a couple minutes ago. We're going to have to solve this as a voltage divider, solve this as a voltage divider, solve this as a voltage divider, solve this as a voltage divider. And then what we'll see is this voltage is dependent on this one. This one is dependent on this one. This one's dependent on that one. So it looks like a complicated circuit, and sure, there are a lot of parts, but you're just going to be analyzing 4 voltage dividers and then plugging one into the other, going back, back, back. And what we're going to end up with is an aggregate amplifier with a single gain. So when we look at this from a design perspective, we're going to be thinking about the 3 amplifiers together as a single amplifier. Okay, so let's categorize these gains. We have the ratio between V-in1 and Vs. We have V-in2 over V-in1, V-in3 over V-in2, VL over V-in3. 4 different gains. We only have 3 amplifiers, though. So what's the 4th value? So the last 3 represent the aggregate gain of the cascaded amps. Okay, you'll see that they incorporate the output stage of each amplifier. The first one is the loss of the gain at the input. All right, so how do we do this? I'm going to go forward to a slide that has some of the math on there, but I'm hoping that this is one, again, hopefully you should be able to eyeball this. By this point, you should have done really well in ELC251-01. This type of stuff, you should be able to spit it out. So, for example, what's VI1? Can anybody tell me with respect to VS? Yes? No, that's the same. Mm-hmm.
Would be VS times 1 over 100. Wait, no, they're different powers, but...
Yeah, no, but I see what you're saying. You're right. It's VS times 1 million over 100,000 plus 1 million. That's what you meant by the 1. Yeah, exactly. Right. Okay. Second one, VI2. It's going to be equal to the input 10 times VI1 times 100,000 over 101,000. Right? 2 added together. Somebody else. What about the third stage? Bingo, exactly. One last one. Yes.
V1, VI3 times 100 ohms over 110 ohms.
Exactly. All right, so you guys have this in the bag. So I can go ahead and just pop up a slide like this. And that is what we get. So you'll see what I did was each one is the output over the input. So VI1 over VS, VI2 over VI1, boom, boom, boom. If you plug in the actual numbers, what you end up with is a loss of gain at the input, 0.909, so about a 10% loss. The gain for the first stage is 9.9. Gain for the second stage is 90.9. Gain for the third stage is a little bit less than 1. This makes sense given what we know about cascading amplifiers. Okay, the gain, we're not really so much concerned with that at the input and the output stages because the main role that they serve is to give us a good input resistance and a good output resistance. The middle is what we threw in here to really boost the gain because the second stage doesn't interface with either the input or with the source or the load. Okay, so right, so what's the aggregate gain? This is going to be the three of these together. And the total gain, including the loss at the input, will be the four of these together. Calculating the, I have the values here. Okay, so if you multiply the three together, you end up with 818 times gain, or 58.3 decibels. And if you include the loss of gain at the input, you get 743 times and 57.4 decibels. So that's the numerical answer. The current gain is actually really easy to calculate because all you have to do is take the voltage and divide by the load resistance. And then once you have the current gain, all you have to do is multiply the two together and it gives you the power gain. So I'll refer you to the textbook to finish that one off, but it's just applying Ohm's law and P equals VI. So cascading amplifiers, the first stage, right, provides the large input resistance. The second stage provides a significant gain. The third stage provides a small input resistance, and we can also say acts as a buffer. Okay, so we're almost done here.